Thank you for coming to my talk. I'm going to be speaking about some aerodynamics of coastal FOREDUNE restoration. So this is sort of a fringe use of computational fluid dynamics. I'm going to try to contextualize some of the background of the study site. This is the Ocean of Dunes in San Luis Obispo County, California. To my knowledge, it is the only place in coastal California where you're allowed to drive off-road vehicles on the beach and in sand dunes. So on the left here, you can see a map of riding area inside of this park where there's very little vegetation because it's been destroyed by anthropogenic activity. On the left. On the right, you can see a picture that I took looking south. I took that picture on top of a vegetated coastal FOREDUNE. And looking south, you can see that there's very little vegetation present. So this is the presence of riders in this area is a very contentious political issue. And this is because there are two EPA air quality monitoring sites downwind of the park. And there's a very strong diurnal cycle of onshore winds that come in at a very consistent direction. And those air quality sites have been routinely observing air quality violations because of mineral dust that comes from this area. So the objectives here are to use computational fluid dynamics to understand the aerodynamics of these dunes and quantify the shear stresses that are being exerted on the topography. Shear stresses are really what we're interested in because the mechanism of dust emission is saltation, which is when sand grains bounce and collide with each other. This releases PM10. And of course, we're trying to drive these simulations with as much measured data as possible. A very classical setup, really similar to a wind tunnel, incompressible Navier-Stokes, steady state, K omega SST turbulence model, and of course using simple foam. I was able to visit the site to collect some wind data with sonic anemometers. This is a small tower that we were able to move around to various locations. In this case, this was collecting the boundary condition inlet data at about 10 hertz at 3 different vertical locations. We're unfortunately not able to do anything higher into the atmosphere because there's an invasive species that nests here, which is also a very contentious issue. However, assuming a log layer at the inlet is a good assumption since we're operating off a maritime boundary condition. Turbulence information is a little more unknown, so we've just sort of extended the measured points that we have up into the atmosphere, and we're able to calculate the turbulence inlet quantities from these two measurements. So we have 6 different restoration strategies that were attempted at this site. So you can see here the T1 through T6 are the domains of OpenFOAM simulations, which overlap on top of these various treatment domains. So T1 is a control where no FOREDUNE restoration treatments were enacted. It was just left alone. In T2, they distributed native seedlings. T3 had native seedlings and, seeds and sterile ryegrass seeds. T4 and T5 had these nodes. These are discs of straw that were pressed into the surface, and those had native seeds and seedlings planted in the middle of them. And then in treatment 6 at the very bottom, we have full coverage of straw, native seeds, native seedlings, and sterile ryegrass. And this is what the shear stress looks like for those 6 simulations. This is the topography. I don't know if I mentioned earlier. The topography was measured using really high resolution photogrammetry. So the ground data set has about 10 centimeters spatial resolution. So you can see that the shear stresses across the 6 different treatments are pretty different. There's not a lot of vegetation in treatment 1. You can see in treatments 4 and 5, there's some straw nodes that are clearly visible. And treatment 3 is really sort of leading the way in terms of native vegetation growth, and it's also the growth of topography. So we do some surface integrals to get a more holistic picture of how effective each of these treatment strategies was. T3 is the clear winner, and that is closely correlated with having the most vegetation and also growing the most surface area, which comes from the vegetation interacting with wind and windblown sand. T1 and T2 performed really badly, but I ran an additional simulation called T0, which was a flat plane that was angled at the same slope as T1, and you can see that there's a really strong improvement. If you just leave sand alone to form dunes, it's actually going to emit less than a flat surface, which is what we get when humans are riding motorized vehicles and camping on the surface. And T4 and T5 did surprisingly similar, even though the nodes in those 2 sites were pretty different in terms of their density. Just to give you an idea of the profile of these different landscapes, all of the restoration treatment areas have this sort of upward sloping as you go inland. So the ocean is on the left here, inland is on the right. And this black dotted line that I imposed over them is a undisturbed natural FOREDUNE that I measured at the south end of the park. Vegetation in that area has been undisturbed, and it has regularly collected sand until it came up to this sort of steady state where the dune rises pretty sharply at the high tide mark. So clearly we have a long way to go before the restoration area has a aerodynamic elevation profile that looks anything like a natural FOREDUNE. And just to revisit T3 and why it was so effective, my colleagues who collected the photogrammetry data using a drone also were able to extract vegetation mask from that, which I projected on top of the shear stress CFD results for treatment 3. And as you can see, where the vegetation is outlined is where topography grows. So the vegetation is actively trapping moving sand. And the vegetation also absorbs a huge brunt of the shear stresses on the surface, which in turn shelters us from emitting more dust. So now that was 2021, and in the next part of this ongoing project, we're going to look at sort of how things evolve over time. Specifically, I'm going to present treatment 4 because it was sort of ineffective, even though it was expected that these nodes, which I'll say were not my idea, were going to form natural looking dunes that would be vegetated. So you can see in the very top panel here, there's the surface before any treatment was implemented. You can actually still pick out tire tracks in the surface. And as we go down through the years, there's overall reduction in shear, and you can see that the plants are growing closer to the shoreline, much better than they're growing. See the pigment. Not a lot of change in elevation. So, like I said before, we have a long way to go. However, you can see that sediment supply is really coming from the beach, which is a geological process that happens in the ocean. And the sediment supply is being tracked pretty early on as it gets into the restoration area, which is starting at a distance of 0 here. However, this is sort of paradoxical because we have we do have a rise in surface area and a reduction in shear through the years for this treatment. However, we know that after 4 years, the straw that was pressed from the surface is still very present, much more so than the geologists put it there and thought it would be. So this reduction in shear is really due to scouring between straw nodes, which turns out to be an effective way to reduce emissions, but is also not a very effective way to grow an ecologically sound FOREDUNE. So I wanted to sort of leave with a picture of what these vegetated FOREDUNEs look like in a healthy state. You can see that here vegetation grows at the sort of head of the dune, so it's a very consistent wind direction. And they're capable of trapping large amounts of sediment in the wakes of these vegetative areas. So the plants on the landscape are really modulating how the landscape evolves under the wind. And we found that shear stresses can be reduced by straw, but in the end result, letting some sand move around early on in the process, while it does increase emissions, is also perhaps a faster path to restoring vegetation, having a healthy work that gets us than so I will leave it there for my time. If there are any questions.
Thank you very much. Yeah, go ahead first. Yeah.
Actually, I didn't present any validation, but yes, the measurements were used here for the inlet boundary condition, and then in some previous work we did do some wind speed ratio validation. Unfortunately, we only have 2 towers, so you can see these locations. We took additional measurements, which I didn't present, and so that tower was moved around, and there was so much dust and sand hitting the anemometers and the electronics that it actually broke the electronics by the end of the few days that it was out there, which is why there's no measurement for T6. So we did get some pretty good results with wind speed ratio, but we can't do direct validation because that one tower had to be moved around, and we broke tens of thousands of dollars. So, yeah, so that was actually really difficult. The Y plus is around 90. We did use wall functions, and on average, like computed with the OpenFOAM's function object, and I ended up using CF mesh just because I was willing to sacrifice. I was having a lot of with Snappy. I was having a lot of boundary layer collapse, and I was worried about the shear stress. So we sort of sacrificed matching the surface exactly a little bit with to get better shear values.
Sorry, I think the mountain back is first.
No, I would really, I've been wanting to go in that direction, and it's just, these are sort of kilometer scale simulations, so it's at this point beyond the amount of computing that I have access to run most sediment models. I think it'd be really interesting to look at the time evolution. No, yeah, so it was drone acquired. The collaborators I have are taking topography measurements every spring and fall at the site, and they're actually continuing to do that. Yes. Yeah, so we really looked for like a characteristic wind speed that was we're looking for like a characteristic wind speed that produces strong enough winds to cause saltation. So this is a wind profile that's just above saltation strength. And that happens pretty regularly every day in the spring, just when we have most of our air quality violations.
Right.
Yeah, so luckily, the vegetation is a few centimeters. It grows very close to the ground because it's constantly getting covered. And that's another thing that I would really love to do some porous media or some kind of momentum extraction for the vegetation. Right now, we're mostly doing it in post-processing, with removing that surface area that's missing.
That's a pause there. Thank you very much.
Okay, so my name is Luca Patruno from University of Bologna, and I presented this presentation about advanced modeling, computational wind engineering, inflow turbulence generation, and modeling of porous elements. I beg your pardon, start begging your pardon because I mixed two things which do not match each other. So basically, this presentation should be seen as an overview of two different tools, one for the inflow generation, one for the porous surface simulation in OpenFOAM, and I will not go into all the full details of the thing. So if you want to know the full details and you're interested, then come to me later. Okay, so the idea is that computational wind engineering grew a lot in the last 10 years. Everybody knows that. I made this graph in 2017, the one you see on the right. And basically, in that exercise, I compared the amount of computational time needed to get some meaningful results for designing wind engineering, computational wind engineering, and the time available at that time. Basically, what you compare are the gray bars with the yellow bars, which is the demand of computational power, let's say, and the other bars correspond to the computational power available in different segments of the hardware. And you see that basically we're catching up now to get some meaningful results using computational wind engineering, which can start competing with the wind tunnel test. So everybody knows that, but the problem is that every time you go in a real project, you always find that there are some additional difficulties with respect to, let's say, the standard tools you have available. And the two difficulties that are very important are the generation of the synthetic turbulence. You need to obtain a boundary layer, an atmospheric boundary layer, and the presence of porous elements, which show these little pores that, meshing all of them is really like impossible in practice. So we need to try to homogenize the porous elements and get some meaningful results from homogenized models. So let us start with the turbulence generation. This comes basically in every simulation in computational wind engineering. There are many different available approaches, and the problem is that there is not really like a standard way to understand what we are targeting. So different techniques are actually targeting different things. So when you go to also compare them, it's really difficult to compare the different approaches. So I'll try to clarify. Many times what you want is to match turbulence intensity or turbulence spectra, which is correlated, of course, Reynolds stresses, coherence, any other metrics of turbulence. In the method I will present you, this is a method designed for computational wind engineering, and we will target mainly turbulence intensity and integral scales. And the other thing is, how do I measure the results I get if they are good or not? Well, there are different approaches to that. One is to measure the adaptation length of the boundary layer you generate. Another one is to maybe put a tower in the middle of the domain and see what the inflow generates on the tower in terms of forces, for example. This is another way to proceed. In my opinion, these two methods are not the best ones. To me, the best method is to check for the field transmission. So if I generate a synthetic turbulent flow, which I want it to be transmitted in the computational simulation, I need to see that that field is actually realized in the computational simulation and is not changed. Because with the other two approaches, you have too many things going on, okay? And you cannot really measure what they're doing. So there are different approaches, of course, recycling method, vortex-based method. I decided to go on spectral methods. Why spectral methods? To me, they are the simplest ones, basically. And, we have differential equations to be solved, basically. And solving differential equation is particularly easy when you have sinusoidal functions. So let's start with the basic representation of synthetic turbulence by spectral methods is the one you see. So you see is basically a Fourier decomposition of the velocity field. So the idea is that once you generate this velocity field, let's say you generate it in some way by finding the parameters of this expansion, of this Fourier expansion, so the P, the K, the Q, and the omega. Well, to be sure that this turbulent velocity field will actually go into your numerical simulation, you need to respect Navier-Stokes equation, and you need to respect the boundary conditions. Otherwise, it will never go into the numerical simulation. We're sure about that. So, of course, if you are able to solve Navier-Stokes equations, maybe you will get a Nobel Prize. So maybe let's go down with our ambition. So we try to solve just Euler equation. And by the way, we remove also the pressure gradients, because anyway, at the inflow, we always basically put zero pressure gradient, so we can get out the pressure gradient from the governing equations. And what you find is that the majority of the turbulence generation approaches, if they use vortex-based methods as a general category, they will respect momentum conservation, but not divergence-free condition. And if you use spectral methods, they will respect the divergence-free condition, but not the momentum conservation, as a general rule. There are exceptions. I show you some exceptions there. So there is the turbulence spot method by Kovnev, which is respecting both. There is the DSM method from Poletto, which is respecting both. And there is the PRFG cube method, which is the method I developed, which is respecting both, and is the only spectral method that does such. Okay, so why insisting so much on this stuff? Well, you can get convinced about the importance of that by taking one single element of this series, and you want this element to be transmitted correctly in the computational domain. So let's do it. So let's take a cube and let's apply just a sinusoidal function at the inflow. The inflow is the one I show you in red. And let's do it with a field, a synthetic field, which is divergence-free and respect Taylor assumption, so linear convection, basically. Then you see, first line, that the field seems to be quite regular. If you plot the field which is transmitted in the simulation and the synthetic one, the one you expect, is the same, basically, and pressure is very low. There is no pressure fluctuation. If you try to do the same thing, removing the divergence-free condition, for example, the second row, you will see that you impose some velocity component at the inflow, but then you cannot transmit this velocity field, and then some velocity components will be just created by the pressure field to balance, to make the divergence free, the field. And so you have no hope that the synthetic field you generate will actually go into your numerical simulation. As a result, pressure fluctuations will be created at the inflow, and you see it on the right. If you do the same thing with by removing selectively the Taylor assumption, you will see something very, very similar. Okay, so you need to respect both in order to have good results. Okay, so what is the idea of this PRFT cube method, which is the method I developed for generating turbulence? The idea is I start from a three-dimensional spectrum of turbulence. This is pretty hard to get, because usually when you talk about turbulence spectra, what you mean actually is the time spectrum. Here it's nothing like that. We want a decomposition of turbulence into the three spatial components. Okay, the time evolution is related to the decomposition in the spatial component by the momentum conservation, actually. So you need to start by having this big turbulence spectra in 3 dimensions, one spectrum for each velocity component. And we have let's say a method, very simple, by multiplication, to generate this turbulence spectra starting from the 9 length scales. Okay, it's an assumption basically, but we can do that. So knowing the 9 length scale, you generate a 3D turbulence spectra, and what you do just is to discretize your wavelength domain. At each frequency, basically, you assign a power for the 3 velocity components. And at that point, knowing the power, you can try to get the P's and the Q's appearing in these equations. Now, very sadly, this turns out to be often impossible. Why? Because there are some constraints to be respected by turbulence to exist. So let us take this case, because many turbulence generation methods will fail this simple test. You ask a turbulence generation method to create turbulence which is different than 0 only on one component. No way you can realize that turbulence. No way. The turbulence generation method should tell you that this is impossible, but many of them will generate a field. Okay, and this is, of course, something that shouldn't happen. Now, investigating this, we found that there are, of course, some criteria to decide if the turbulence can exist with that power or not. And we created a method to basically correct the spectra in order to change the turbulent content as little as possible and still get a real result that can be realized. So I don't go into the details of that, but the idea is that you come out with a turbulent field, which is characterized by the right intensity, the right length scale. It's divergence free. It respects Taylor assumption of frozen turbulence, so linear convection, so an approximation of the momentum equation. You're very happy. You go there, you apply at the inflow, and you see that fluctuation of pressure still occur at the inflow patch. And that is unavoidable. And I explain you why. Because the synthetic turbulence you generated doesn't respect the boundary conditions. So if you go at the boundary of your inflow patch, you will see that you might have some velocity components that, for example, let's assume that the side patches are symmetry or a wall. You cannot have a velocity component normal to that wall, but your synthetic flow doesn't know about it usually. And so you want that component, but you cannot generate them. And this will create pressure fluctuations again. So what we did was to create this procedure, which is called VBIC, variationally based inflow correction method. And the idea is that I generate synthetic turbulence, then I assume that I can correct this synthetic turbulence. So I see the total velocity applied at the inflow patch as the synthetic turbulence plus a correction. And I get a correction requiring for it 2 things: to be of minimal modulus, so that the correction is as small as possible, but still requiring the field to be divergence free and respect boundary conditions. So I don't go into the details of that, but you can actually solve for this problem, and you will get a partial differential equation to be solved on the inflow patch which will give you the corrections to be applied to respect boundary conditions with your field and be divergence-free with your field. So let us look at the results of all of that. On the left, you see a tube like before in which you inject a wave, just one wave of turbulence, one velocity fluctuation, and this wave is not divergence-free, so it is creating pressure fluctuations. The same wave, you make it divergence-free, you apply at the second tube, you see that the pressure field is clean in the center, but it's giving fluctuation on the boundary of the tube. If you apply VBIC with the same field you have on the left, you remove basically completely all pressure fluctuations. Okay, it seems to work. So we applied every time we generate a boundary layer. This is, for example, a boundary layer flow in the vicinity of the center of Milan. You can see the spectra which are generated in the profiles, and you on the bottom figure on the right, you see the difference between applying and not applying these corrections. If you don't apply corrections, this is the long wind evolution of the root mean square of pressure. We see at the inflow you have a lot of root mean square of pressure that then goes down after a while. This length is usually a couple of length scales. If you do apply correction, you start already from a very low value of pressure fluctuations. Okay, so this ends the first part of the presentation, the one related to synthetic turbulence generation. We go to the second part, which is porous surfaces. So you generated now your nice boundary layer, and you bump into these cases, which are becoming increasingly common. The facade is porous, or you go on a bridge deck, and the bridge deck windscreens maybe are porous. And with CFD, it's very hard. In wind tunnel tests, it's very hard as well. You have two options in CFD. You can have porous zones, so you make a thickness, you really mesh in the volume a porous material, or you make a pressure jump, basically. Pressure jump is much easier. The problem of pressure jump is that, of course, it's a homogenized approach, so it assumes a separation of scales. It does not take into account the production of turbulence at this grid, at this porous element, but most importantly, it takes into account only forces which are exchanged between the barrier, the porous element, and the fluid along the normal direction of the element, of the porous element. You might have many cases in which this is not the case. There are shear stresses, basically, forces exchanged on the plane of the barrier. I will show you some example. Like, for example, you will see here, the case denoted as LC is made by small lamella. These lamella are exchanging forces surely not in the normal direction of the surface, of the mean surface of the lamella. So we need to tackle that. So the idea was to create an approach which was simple enough to not make the parameters explode and to be basically an evolution of the pressure jump. And a very important characteristic we wanted to give to it was that it should have been able to reproduce some limit cases. And these limit cases, summarizing, is if I have objects which are a very far distance from each other, they will not interact. So I need the normal loads of an object which do not interact. And if I have like lamella, like this one's, closely spaced, basically the flow is obliged to exit the lamella in the tangential direction. And this gives rise to the possibility to find an analytical solution because the flow is deflected in the direction of the lamella. And then we want this to be reproduced exactly by our. So the idea is that basically you have this model. I don't detail it too much here. If you want, you're interested in detail. And you basically take a section, a small element in periodic conditions of your barrier. You calibrate some coefficients, and with this one you enter into this procedure, and basically it gives a pressure jump, which has the ability also to deflect the flow to account for shear stresses. So let us have a look. This is a barrier, a ground-mounted barrier, and we tested different barriers. We tested it with a different amount of number of elements composing this barrier, because this approach is true when there are many, many elements. Just if there are 3 elements, you just model it explicitly. And the idea is that we made experiments with this triangle, with these flat elements, and with lamella. I show you the lamella because those are the most interesting one to look at. So this is the result. So the left column is lamellae, many lamella, like 50 lamellae. You don't see them because they're very small, but there are 50 lamella explicitly modeled in OpenFOAM. I need to warn you, these are 2D Urans, this one, but still, we needed to make 50 lamellae to deflect the flow exactly in the direction we wanted. And in the top row, they are pointing up, and in the lower row, they are pointing down. And you see that this has a dramatic effect, of course, on the flow that is created downstream the barrier. Now, the second row, there is no lamella, is our homogenized approach in which we calibrated the laws which are governing this pressure velocity jump, basically, in an analytical way, okay? And the third row is still our approach in which we calibrated the coefficient of the model starting from a simulation of the barrier taken in periodic conditions, so a little element of the barrier. We deduce the parameters of the model and we apply the model. And you see that if you compare the left images to the right images, basically they are the same, but the computation, of course, is truly not comparable because in the first one you have 50 lamella to be simulated, and in the second one you have basically a pressure jump with some more features. So summarizing, I present you an inflow generation method, which is called PRFG-Cube, which has the ability to be divergence-free and to respect momentum conservation. I told you that this is not enough to avoid pressure fluctuations at the inflow. You need to also correct for boundary conditions. And by the way, if your divergence-free field goes inhomogeneous, you will anyway have some inaccuracies in the procedure. So you need another procedure. And these are the procedure we created. One is called VBIC, and it will help you in moderating a lot the pressure fluctuations. And VBIC can be used also with other turbulence generation method. It's not restricted to PRFG2. You can use your own generation method. And finally, I showed you an evolution of the pressure jump, which we call pressure velocity jump, in which we basically have a full description of the forces exchanged between a porous element, porous surface, and the flow, taking into account both normal and tangential forces exchanged by the fluid and the porous element. You find implementations for OpenFOAM of both methods at our website. There is documentation, there is everything. If it doesn't work, something, please let me know, because it should work everything. And the documentation is relatively well written, so it should be possible for you to use it. Thank you very much. No, I mean, it would be great, but no, the method at the moment is implemented so that you keep the 9 length scales, and it will generate a spectra in a standard way. And this spectra is maybe not the most physical one, but it has the property that the marginal spectra are correct. Okay, so it's no worse than just applying the time spectra, let's say. And it will only require the 9 length scales. And usually when we do these things, you know what is your LUX, and you know the others by percentage. So maybe you assume LUX is 100 meter, and the other will be around 50, 30, 60, something like that. This one. What's the problem of the pressure at the boundary? Yeah. No, sorry, I didn't understand the question. Why you ask why pressure fluctuations happen to be at the boundary? Yeah. No, more actually, I ensure the consistency of the velocity, because the synthetic turbulence generation methods, they don't know about boundaries. It's like infinite domain, right? And you will have some velocity components which are maybe normal to a wall. And you need to suppress that velocity component. But of course, you cannot just put it to zero, because otherwise your field will get destroyed, basically. And this method is able to give you a smooth, let's say, correction, which ensures that your boundary condition will be respected. The total velocity you apply will have the right boundary conditions. And it will ensure at the same time that the velocity you actually applied is divergence-free, taking into account also momentum conservation. So basically, it acts as a filter between, it's an intermediate layer between synthetic turbulence, whatever generation method you use, and your simulation that ensures divergence-free condition and boundary condition to be respected. Yeah. But those are, no, wait, the amount of pressure fluctuations is insane. I mean, if you look at, you look at the here, I mean, these pressure fluctuations are not natural. These pressure fluctuations is because it's the simulation is not doing its job. Okay, it's not the natural pressure fluctuation. You can see it on the graph. I mean, you see the lower curve, the bottom is not zero. We start from 0.05, okay, a little bit more. And then it goes to 0.04. And that, for this particular simulation, was the level of pressure fluctuations which is expected into the turbulence it's generated. Yeah, that is related to the velocity spectrum, but the other one is out of scale. Yeah.
This conversation in the public.
Yeah.
Conscious that we have to keep the time.
Yeah. Thank you very much.
Thank you very much.
Hello everyone, my name is Jérémie Gaucher. I'm a hydrotechnical engineer at Hydro-Québec, which is a public utility based in the province of Quebec, Canada. I've been using OpenFOAM for roughly 10 years now. Maryse Page, my co-author, is also at Hydro-Québec. She's a researcher at our research institute, and she's used and contributed to OpenFOAM over at least the last 20 years. The topic of my presentation today is about application of OpenFOAM to dam safety. I'll present you a recent project in which we used OpenFOAM to verify the safe passage of various flood events through a hydropower facility, through its spillways, and how we used it to evaluate the water levels. My presentation will be outlined as follows. I'll briefly summarize our business and how we use OpenFOAM for various engineering applications. I'll then describe the hydropower facility of this study and why we had to do a hydraulic review. Then I'll go over various aspects of the model, such as geometrical representation, meshing, boundary conditions, solver parameters, and some cues on pre and post treatment. I'll then briefly go over how we validated our model and also some of our main findings. And finally, I'll show you some interesting results on a small case study that we did at the same time at the same facility concerning dam overtopping, which is sometimes overlooked. Hydro-Québec is a publicly owned power utility. Our power generation is completely out of renewables, mainly hydropower. Our current installed capacity is 37,500 megawatts generated through 62 stations using 340 hydro generating units. This is possible through the use of over 660 dams and 29 large reservoirs. We operate roughly 100 hydraulic control structures, such as gated and ungated spillways, various types of fishways, and several river sills. And my presentation is mainly about these latter types of structures. Researchers at our research institute have used and contributed in the past to OpenFOAM, mainly in the turbo machinery domain. But starting in the early 2010s, we initiated a project to evaluate whether OpenFOAM could be used to accurately model flows through hydraulic structures. These structures have their main characteristics is that they operate with a free surface flow on both sides, sometimes with a transition in a pressurized way, such as bottom outlets. But in cases such as spillways, the flow is at free surface atmospheric pressure upstream, downstream, and through the structure. So we needed a solution that was multi-phase, such as the interfoam solver. And during the project, we evaluated various things, such as the best meshing practices, what were the optimal numerical parameters for this kind of applications, what were the best boundary conditions to use, as well as some pre and post processing options. We also did some extensive validation against measurements from both model and prototype scales, and we were quite satisfied with the result. Early progress was reported at the OpenFOAM Workshop 9 in Croatia in 2013, and the project was completed in 2020. OpenFOAM is now used in a production setting. I've summarized here the applications of OpenFOAM to hydraulic structures in 3 families. We update and validate spillway rating curves of our spillways that are either in service or projected for construction. This allows for estimation of water levels during various flood loadings and generation of other quantities such as pressure distributions for stability analyses. We also evaluate cavitation indices near spillway gates and sills and along chutes, as well as rock scour potential downstream. There are also other applications in the environment and health and safety domain, such as fish ladders, transient and side power station intakes, and also safe conditions for diving. The studied hydropower facility is shown in the picture below. It was built over a 100-year period, starting in the early 1910s. The average head is about 24 meters. And it's being used at 2 different powerhouses, one built in 1916 and the other in 2004. On both banks, there are 3 spillways in the center, a main and a regulating spillway, and also an emergency spillway using stop logs. The facility was designed to transit a probable maximum flood, or PMF, of 12,350 cubic meters per second with all gates open and the stations offline. And there was also some overtopping allowed for this case over the intermediate gravity dam. For North American standards, the site is quite old, maybe not so much for Italian standards. You can see the fall in 1828 was not developed. The first developments appeared in the late 19th century with a paper mill on the right bank and rudimentary wood crib dams. That development expanded in the early 20th century and eventually was replaced by a modern concrete dam and powerhouse in 1916, which is what we call the old station. The left-hand side of the facility was completely rebuilt in 2004 with the new spillways and new powerhouse, and the old spillway was demolished underwater and is now inside the reservoir, which makes it quite an interesting case considering the complex bathymetry now upstream from our dam. You can see on this picture a scan from 2021 where we see the first and second generation of various structures that you can see on the old pictures that are now underwater. They've been either abandoned or partly demolished and are now inside the reservoir. The third generation of dam is now downstream from the original fall. And before it was constructed, an extensive physical model study was undertaken to make sure that all these features would not hinder capacity. Several parameters have changed since the construction of the new powerhouse. The PMF was revised up by about 500 cubic meters, which means several of the dams will be overtopped now in that condition. There are upcoming works, such as the decommissioning of the 1916 powerhouse, which will now act as a dam. And the right gravity dam will also be upgraded, and any other work necessary to contain the new PMF. There is also some unknowns, such as the elevation of the demolished spillway that is underwater, as well as some uncertainty about the capacity of the intermediate dam when overtopped. So it was a good candidate for OpenFOAM. It's cheaper and faster than building a new physical model. There's no licensing constraint, and we appreciated some of the flexible meshing options for this particular case. The geometrical representation of the facility was built using an assembly of a digital terrain model and dam solids. The terrain was built from various bathymetric surveys, stitched with airborne LiDAR on both banks, and assembled using Global Mapper exported to STL surfaces. The dams and power stations were drawn from 35 different engineering drawings. Details such as bridge, girders, gates, and guardrails were rendered using AutoCAD 3D. The mesh was produced using SnappyX mesh. We used OpenCFD's version 2106 on 48 cores. The domain is shown on the upper left image. It spans 640 meters wide, 700 meters long, and 60 meters high. The base resolution level 0 is 4 meters in the air phase, and the level 4 resolution is 25 centimeters near structures. We added 3 layers on spillway chutes and pillars. The thinner layer is 1 centimeter near the wall. We found it improves agreement with measured flow rates to add these layers on spillway chutes. There's also a vertical refinement near the water surface using a topo set extraction of those cells and a refinement in Z only using refined mesh. We found it improves free surface resolution with a marginal computational overhead. Finally, the mesh is renumbered and our final mesh is 4.4 million cells. The boundary conditions are shown in the table down right. I extracted 3 of the main ones. The upstream patch is a submerged patch, so it's below the free surface elevation. It's a flow rate inlet velocity type on U. In this case, I'm showing you a table because we were ramping up discharge. Downstream, we're imposing a tail water level using a fixed flux pressure on PRGH. And on the walls, since we're not modeling the boundary layer, we're using a new TU rough wall function to be used with a K omega SST turbulence model. The parameter that changes here is the roughness height. We use 5 millimeters on concrete surfaces and 15 centimeters on the riverbed. This 15 centimeter we arrived by doing a few sensitivity analysis. We use the InterFOAM solver, same version as Snappy, so V2106 for this project on 120 cores with a K omega SST turbulence model. We're only working in quasi-steady conditions, so we left the DDT scheme at Euler, and we're using iterative solvers. The CFL condition is limited to 1 in this case, and some runtime details. We have a time step of about 2 milliseconds when simulating the PMS scenario, which gives us a time per outer iteration of about 0.3 seconds and a runtime of 40 hours to reach stable conditions. Various results were followed using function objects. You can see water levels were probed at 3 locations: upstream of the 1916 powerhouse, upstream of the 2004 powerhouse, and upstream of the demolished spillway. We used probes on PRGH, so our probe location is under the water surface near the bottom, and to obtain the free surface elevation, we add the water column to the probe location. We found it was more accurate to work this way than to locate the interface at alpha equals 0.5. We extracted the flow rates at each individual sluiceway using phase zone patches and did a sum on field row phi to obtain the discharge. You can see 2 graphs of the monitoring of this simulation that shows that stable conditions were reached roughly around 1,000 seconds of simulated time. All other visuals were generated using PRView. Our model was validated against the physical model from 1995. We had measurements of both spillway rating curves and head losses on both sides of the demolished spillways between measurement points Z7 and Z11. So we validated both. The agreement is within 1% for the spillway rating curve, which is excellent. We're usually very satisfied below 5%. And the head loss reduction at a 1 in a 10,000 year flood of 8,225 cubic meters per second is within 5 centimeters of the head losses from the scale model. Then we proceeded with the simulation of various scenarios. I'm showing you here an example of the new PMF, which is 12,893. Up left, you can see just an isometric view of the velocity inside the sluiceways. At the bottom left, you can see that the slices taken from the regulating spillway and secondary spillway show that the water touches the bridge deck. This has an incidence on the flow rate. The actual capacity has decreased since there's contact with the various structural parts of the dam. The upper right figure shows the velocity in plan view. You can see the acceleration over the old island and demolished spillway, which is the reason why there is a head loss, and the evaluated levels are shown on the bottom right. One aspect that was looked at was the actual profile of the demolished dam compared to the theoretical profile that was considered during the scale model study. Following the scan from 2021, we found that there was an increase in flow area since some of the old dam was over-excavated. So this is a good thing as it decreases head losses and will diminish slightly water levels during a PMF. You can see both the axis of the old dam and these profiles, as well as the head loss that's now updated using the new bathymetry, which shows that head losses are less than expected. However, this is not sufficient to diminish water levels during PMF sufficiently to avoid dam overtopping. Which brings me to a small case study of the intermediate dam. Considering the water levels are now 1.5 meter above its crest, we evaluated what was the actual overtopping discharge. As we understood that this dam was assumed that it would function as a broad-crested weir during the project. However, there are several hindrances on the crest now. There's an upstream guardrail, a downstream guardrail, because the dam is used as a bridge. There are some ducts and cable shells on both sides. There's a small instrument shelter. So we're expecting discharge to be less than the theoretical discharge. So we built a small 6-meter wide model of that dam with a resolution of around 3 centimeters near the guardrails to evaluate the discharge. The figure on the left shows the main results we got. The ideal broad-crested weir, which is the image on the top right, shows what it would be like if there were no guardrails and no hindrance on the crest. The coefficient of discharge of those kinds of spillways is usually around 0.4, as can be shown in the figure. Experimental data from Smith 1995 show that the discharge coefficient for that dam would be around 0.37. And the OpenFOAM simulation without the guardrails is in agreement as well with discharge coefficients that are very similar. However, when we add the guardrails in the flow, you can see that the flow changes aspects. There is a contraction at the upstream guardrail, acceleration on the crest, and then there is a small hydraulic jump and another contraction at the downstream guardrail, which means that when we integrate flow at the center location, we obtain unit discharges that are much smaller and a coefficient of discharge that is about 50% less than the theoretical coefficient of discharge for this kind of structure, which means that there's a big reduction in capacity when considering overtopping with obstructions on the crest, and we believe that it is not a good practice to assume that this kind of dam will be able to contribute to capacity during large floods. In conclusion, for this particular hydraulic study, we found that OpenFOAM reproduced adequately experimental measurements. It was also allowed us to better represent some of the flow interaction with structures that we usually don't take into account in our studies. The meshing was sufficiently flexible to represent most phenomena of interest at various scales, and our calculation times remain reasonable. Some of our future work that are planned with OpenFOAM is to be able to generate two-dimensional hydraulic parameters such as fluid number, depth average velocity, bottom shear stress. And the challenge here is to be able to generate those by doing a vertical integration on the irregular grid and storing that data in every single cell in the mesh to be able to manipulate and represent it in various ways in ParaView. So we're still reflecting on whether we should do that using a ParaView Python script or function object or any other work that some of you might have realized already. We also would like to improve our meshing technique. We don't always control the quality and the type of STLs that we work with, and sometimes it'd be very interesting if we could mix both explicit and implicit edge detection in SnappyXMesh. I don't know if it's possible. There's also we're also looking into ways to be able to use a different number of layers on different surfaces within the same mesh. Which concludes my presentation, and thank you for your attention.